I'm going to go ahead and start recording this session. I recorded the session we had on Tuesday, and I posted it on my Google webpage, and I'm going to be doing that with all of these sessions. Today's class is actually, in theory, sort of optional. We were told not to necessarily do a live lecture, but I decided I would, and I'll just post these this video clip later, and people who aren't here live can watch it at any time later on. But we're not going to do a lot of new material today. I'm going to start by talking about the midterm and sort of where we're at with homework and things like that. Then I'm going to just do a couple of things that are based on this material up here about linear transformations to just kind of wrap that up. Then I'm going to take some homework questions if you have any. And then I'm going to go through some group works with you that we never got to do in class. And we can kind of use this as a little bit of review, actually, for the midterm. I think looking at those group works would be great. Okay, so let me start with the fact that you guys should have received your homework number 12 back already. I tried to email everybody last night. My grader attached comments and your scores on the last page at the bottom of that assignment. So I emailed it back to you. I hope you got it. If you didn't get that email, be sure to let me know. Send me a message so that I'll be aware of that. My grader is currently working on the homework that you turned in on Tuesday already. I'll get those back to you as soon as he's done with those. And then there's another homework that's due tonight. So I'll be looking forward to receiving those. I sent you an invitation to submit those into a Dropbox folder already. So if you didn't get that or you're not sure what to do with your homework, shoot me an email or ask me later, and I'll be happy to try to help you out with that. There will be another homework that'll be due next Tuesday, which is based on section 6.1. And by the time we're done talking today, you'll have all the material you need for that. And you'll also have all of the material that's going to be covered on our midterm. So let me take a quick minute and talk about the midterm again. There's been a couple of changes. The date is still the same. We're going to take this midterm 1 week from today on Thursday, March 26th. And I'll be sending you through email a copy of that midterm shortly before noon on Thursday, March 26th. So you'll be getting an email and you'll need to make sure you can load up that exam. You don't have to print it out, but you need to be able to look at the questions, obviously. And what I would like you to do during the midterm is be logged on to your Zoom channel right here, like we are right now. I'd like everybody to be logged on to Zoom for that. The midterm is going to cover all of chapter 4 except for 4.7, which we did not cover, as well as 5.1 through 5.3 and 6.1. All of that is in my review packet that is posted on my website, so you should be able to find that and review it later if you didn't write that down. I am going to give you the Graham-Schmidt formulas, which are what you needed for some of today's homework, for instance. It's what we were talking about on Tuesday. So I'm going to give you those formulas. Other than that, pretty much it's going to be closed notes, closed book, closed calculator, all the same usual rules that we have for our exams. Okay. Also, I had said that I was kind of going to let you work on this thing for a long time, but I realized that there's some students in the class that actually have to go to another Zoom meeting at 2:30. So I am going to have to change my mind on that. I'm sorry about that, but I'm going to cut the exam off at around 2:25. So you'll have about 2.5 hours to take the exam. Hopefully that extra half hour is enough to account for any technology glitches that you may encounter. I'm going to be very lenient with you about, I understand it may take a minute to get the pictures taken and submit it to the Dropbox folder, but I am going to have to cut you off around 2:30. So please don't be expecting to work on this thing kind of indefinitely. I'll want you to submit your exam next Thursday exactly the same way that you submit homeworks now, which is through Dropbox into a folder that I will be inviting you to join. So that's how that will work. Let me see, what else should I say? Review sessions. I always like to do review sessions for my exams. I've been told not to really do a lot of live stuff over the next few days anyway. So I've decided to just ask you to watch my my YouTube links with the review sessions from when I taught this class last semester. I think they're pretty good. You know, we spent like about 2 to 3 hours doing a review session. So you can just watch last year's review session. Those students had to learn exactly the same topics. It was exactly the same problems. So you can watch them. And of course, you can make some notes to yourself. If you have questions about anything in any of those review sessions, you can then ask me later in virtual office hours. Make sure, by the way, if you're looking for me during office hours, you shouldn't be on this meeting channel. This is just for our 250B class meetings. I have a different meeting ID number, which I reminded you about in an email about a day or so ago. And what I basically do for that, I just turn my computer on. I go into that meeting room. I turn the chime on so I can hear when somebody comes and goes from the room. And so I just kind of pay attention to it that way. So just come on into the room. If I happen to wander off for a moment, just hang tight. I'll come right back to my computer and we can start talking. So that's for the virtual office hours. Okay, so that's all I've got to say about the midterm so far. I'm not going, after I kind of go through a couple quick things here at the beginning today, I'm not going to be doing any more actual new material or lecture material until actually after the midterm, which means after spring break. So there'll be a little bit of a break in the lecture material. Because I'm not being allowed to sort of go full blast into my lecturing though during these Zoom sessions, you know, today and next Tuesday, I am going to ask you to watch about 5 YouTube videos over spring break. In total, it maybe adds up to about 2 hours of time, so it's like 1 class period. I would put those videos up now, but there's no need for you to watch them now because they involve material that will not be on your midterm. So I think what would make more sense is to focus on studying for the midterm right now for the next 7 days. And then I'll post those YouTube videos and you'll have the whole spring break to watch them. And there will be homework based on those videos that'll be due when we come back from spring break. And of course, we'll have time to talk more about that then. Okay, so those are the main things that I have to say in terms of the logistics and kind of where we're at right now. I wanted to pause for a moment and see if anybody might have any questions. You can certainly unmute yourself and ask me. Does anybody have any questions about either the midterm that's coming up or anything about that, the logistics here, or any questions about Zoom so far? Oh, I see a question here. Is there going to be a Zoom meeting next Tuesday? The answer to that is yes. I am going to do exactly what I'm doing right now, which is to sort of have an informal virtual office hour, which is what I'm calling this. It would be great to come next Tuesday because I'm going to answer questions on your homework assignment that's due that day, as well as anything else. If you've been studying for the, midterm and you have any questions, you can certainly come on Tuesday and ask them. And by the way, again, the second midterm is next Thursday. That's March 26th. So right now, what I'm talking about is Tuesday, March 24th, 2 days before your midterm. I am going to be here at that time to answer questions on homework, answer questions about your studying. Maybe we'll do another group work. It'll just be a very a casual time. I will not be doing any new material next Tuesday. So you can rest assured that everything will be covered pretty much by today. So you have a whole 7 days to kind of get on top of all of this stuff. The only downside is that over spring break, I am going to ask you to watch some videos to kind of make up time. I want to make sure we don't get crunched at the end of the semester to finish everything up. Okay, does anybody else have any questions before we jump in today? Okay, if not, I'm going to go ahead and recap what we did on Tuesday and just show you one last little application of it. After we do that, it's going to be mostly just answering questions about homework and doing some group work. Okay, so up here on the board, you see that I've put up a reminder about linear transformations. We have two vector spaces, V and W, and a function between them, a function between these vector spaces is called a linear transformation if it respects addition and scalar multiplication. Okay, so T respects addition, T respects scalar multiplication. So if I ask you to show that something is linear, if I ask you to verify that some given transformation is a linear transformation, you're going to check these two things, right? You're going to check that T respects addition and scalar multiplication, those two things. Okay, we did some examples of that in our last class meeting, so I'm not going to dwell on it too much right now. I'll let you guys practice a little bit in the homework for Tuesday on that. Now, also, don't forget on Tuesday I mentioned this zero vector check. So if T is going to be linear, then the zero vector has to get transformed to the zero vector. So there's a zero vector in V, there's a zero vector in W, and the zero vector of V has to get mapped to the zero vector of W. If that doesn't happen, if the zero vector is not mapping to the zero vector when I apply the transformation, well, then T is not linear, and you can just stop and say that, right? You can save yourself a little bit of time, okay? If the zero vector check is satisfied, then you do have to go back and verify that T respects addition and scalar multiplication, okay? Are there any questions on that so far? This is just a review from Tuesday. I like to draw pictures, actually. So I put a little picture here at the bottom of my whiteboard where I kind of draw this little circle for V, and then over to the right I have another circle for W, and T is just a function. So it's just like having arrows that go from the left side to the right side. You have inputs and outputs to this transformation. Notice that I put my zero vector for V and my zero vector for W at the bottom of those two circles. The zero vector has to be mapped to the zero vector, right? That's our zero vector check. And then these other blue arrows that I drew is just showing inputs and outputs, right? And that's what a function does, right? It takes inputs to outputs. But it must do so in a way that respects the vector space operations of addition and scalar multiplication, okay? So with having said that, I'm going to go ahead and erase this unless there's any question here. And I'm going to just throw in this one little extra thing that I didn't quite have time for on Tuesday, but which is really very important. So I'm going to make a little remark for you guys right now, and then I'm going to explain it, okay? So let me get my notes over here in front of the whiteboard really quickly. Okay, so I'm going to make a remark. This is something I did not get a chance to do on Tuesday. And again, guys, let me know if you can't read anything on this board, okay? All right, great. So here's my remark. If we have a basis, let's say the set V1, V2, ... up to Vn, if that is a basis for V, right? So if we have a basis for a vector space, and if we know already what T does to that basis, so if T of V1, T of V2, up to T of Vn, if these are given, okay, so this is the last little bit we need, and we'll be good to go for the midterm, right? I just want to get this last little thing in. So if somebody tells us already what my transformation does to the basis for V, well, then we can compute. At that point, we can compute T of V for any vector V in the vector space V. This is my remark, right? We can calculate T of anything if we just know what T of the basis is. You know, the idea behind that is, you know, if I want to know what is T of any vector V, so this is now explaining, I just want to explain why this remark is true. If I want to know what T of V is, take a look. T of V is going to be what? It's going to be like T of C1 V1 plus C2 V2 plus ... plus Cn Vn, like that. Because every vector in the vector space can be written as a linear combination of the basis. This is the power of a basis, right? It spans V. So every vector in V can be written as a linear combination like this. But remember, guys, that linear transformations respect addition and scalar multiplication. And when you see this linear combination inside those parentheses, you see a lot of addition and scalar multiplication going on. So T respects all of that. In other words, you can totally bust this thing apart and write it as, you know, C1 times T of V1 plus C2 times T of V2 plus ... plus Cn times T of Vn. So you can literally break it into pieces. And now if you already know what T of V1 is, what T of V2 is, and what T of Vn is, well, then you now know what T of V is, right? This is a very, very powerful idea. So it's one of the main reasons why we care about having a basis for a vector space. Because as soon as you know what your linear transformation does to that basis, in other words, as soon as you know what T of each basis vector is, then you know what T of everything is. Okay? Does this make sense so far? I'm hoping I'm making some sense. Okay, so what I'm going to do is show you an example of this. Actually, I'm going to show you two examples of this. One of them is pretty easy, and then the second one we have to work a little harder on. Okay, so here's an example. Here's an example. So the first one is this. Suppose that T, okay, this is going to be my linear transformation. T is going to go from R2 over to P2 of R. So I'm going to be inputting like pairs of real numbers. I'm going to output quadratic polynomials. Okay, let's assume that this is linear. Let's assume that it's linear, but I didn't give you the formula for it, right? It's not like we can check it right now because we don't know what the formula is for T of AB. But let's assume we know that we have a linear function, something that respects addition and scalar multiplication. Okay, so let's assume that T of 1, 0 is equal to 3x minus 5, and T of 0, 1, I'm going to try to add a little bit more over here on the far right side. T of 0, 1 is 7x squared plus 2x plus 1. Let me just move this chair a little bit out of the way. Can everybody see that all right? Let me know if it's not clear. T of 1, 0 and T of 0, 1. And now my question is going to be, find T of any other point AB. This is what we're going to ask. What is T of any point A comma B? And we're just going to use that idea from the remark at the top, right? If I tell you what t of 1, 0 is, and I tell you what t of 0, 1 is, I have told you what t does to this basis of R2, right? The nicest basis for R2 is just 1, 0 and 0, 1. So I've told you what those values are, and I'm asking you, what is t of anything else? Well, the answer is pretty straightforward. All I have to do to find t of AB, so this is my solution right here. All I have to do to find t of AB is I have to realize that I can break AB into 1, 0 and 0, 1. So it's going to be what? It's going to be A times 1, 0 plus B times 0, 1. Okay. And now, so just inside the parentheses, if you work this out, this thing in the parentheses is just A comma B. Just a second, I got somebody coming into the room here. I'm just going to let them in. Okay, so I'm trying to find t of AB. I know that AB can be broken down in terms of my basis as A times 1, 0 plus B times 0, 1, right? And now I can use the fact that t respects linear combinations, right? So if t respects addition and it respects scalar multiplication, then it respects linear combinations. Okay, so t respects linear combinations. Let me go ahead and write this down. This is A times t of 1, 0 plus B times t of 0, 1. Okay, so I'm just breaking it apart in that manner. And now I can just plug in what we were given in the first place, right? This is just A times 3x minus 5 plus B times 7x squared plus 2x plus 1. That would be a perfectly good answer. That would be a perfectly good answer. So does anybody have any questions on that one? I'm going to do another one in a minute, but this is sort of an easy one to start off with, right? As soon as I tell you what t of 1, 0 is, and I tell you what t of 0, 1 is, then I can find t of anything else. Okay? Any questions so far? All right, great. If for any reason I'm going too fast, you'll be able to go back to this video later. Another option is to just take a snapshot of the screen here. It's got everything we've been talking about for the last 10 minutes on it. And that's another way to sort of keep up a little bit. But yeah, I will be posting this video later on today. Okay, let me do. Yes, question?
This is Matt.
Hey, Matt. Yeah, what's up?
So would it be incorrect to do A times 0, 1 plus B times 1, 0?
Yeah, that would not be correct, because if you look at how where the A and the B are positioned in the ordered pair there, you see that the A is in the first slot and the B is in the second slot. So when you bust out the A and the B, you have to make sure you're writing down the correct leftover vector. So the A has to be multiplied by 1, 0, and the B has to be multiplied by 0, 1. Yeah, that is required to be in that way.
Okay.
Do you see that? Just imagine, like, remember when we were back in the old days when we were like busting out the variables, right?
Yes.
When you bust out the A from the pair A comma B, you leave yourself with a 1 in the first slot and a 0 in the second slot, because the A is only in the first slot. So that's why the A has to be multiplied by 1, 0 here.
Okay, thank you.
And then similarly, the B has to be multiplied by 0, 1.
Okay.
All right, great. Let me, I'm going to erase this now, okay? And then we're going to try one more example. This next example is a little bit trickier. It's a little bit messier is really what I should say. It's the same idea, but it's a little bit messier. So this is example 2. Let's try an example here. Let's assume that t goes from R3 to R3 is linear. Okay. Oh, by the way, if I have a transformation from Rn to Rm, I just want to remind you from Tuesday that that means that we can represent it using a matrix. Okay. By the end of doing this problem, we'll be able to write down the matrix. Okay. So there's a matrix. In this case, it would be a 3 by 3 matrix that is associated with this linear transformation. Okay. Let's keep going though. Let me assume that t of 1, 2, 0 is equal to 2, -1, 1. And I'm also going to assume that t of 0, 1, 1 is equal to 3, -1, -1. And I'm going to assume that t of 0, 2, 3 is equal to 6, -5, 4. And the question is going to be, find t of A, B, C. Can everybody read that? All right. So the thing that's tricky about this one, guys, compared to the last one, on the last example, I told you what t of 1, 0 is, and I told you what t of 0, 1 is. This time, I told you what t does to 3 relatively not so nice points, right? T of 1, 2, 0, t of 0, 1, 1, and t of 0, 2, 3. All right, that's not as nice as you would like. In fact, when you're trying to figure out t of A, B, C, right, if we just use the same idea from the last example, that would just be A times t of 1, 0, 0 plus B times t of 0, 1, 0 plus C times t of 0, 0, 1. If I just do the same thing I did before, where I just bust out my variables, A, B, and C, and then use the fact that t respects those linear combinations, that's what I would have on the right-hand side. But do you see the problem here is that we were not given t of 1, 0, 0. We were not given t of 0, 1, 0, and we were not given t of 0, 0, 1. We were given values of t for 3 other points, right? So what we are going to have to do here is we are going to have to figure out from those 3 other points, what is t of 1, 0, 0, what is t of 0, 1, 0, and what is t of 0, 0, 1, okay? And this involves a little bit of fumbling around. I'm not going to lie to you about this. It takes a little bit of work to figure out what t of these 3 values that we need are actually equal to. Let me give you an idea, a little bit of what kind of fumbling I'm talking about. You see, I happen to notice that if I take t of 0, 2, 3, and I subtract I subtract 2 times t of 0, 1, 1. So just take a look at that with me for a second. If I subtract, so if you take 0, 1, 1 and you multiply it by 2, you get 0, 2, 2. And if you take 0, 2, 3 minus 0, 2, 2, you actually get 0, 0, 1 over here, right? See, so I can make 0, 0, 1 out of 0, 2, 3 and 0, 1, 1. This is what I'm doing right now. And I've got somebody else coming in here, so let me open the room up. Okay, great. Again, for any of you who are showing up a little bit late, don't worry. I'm going to post this video later this afternoon, so you can go back and watch the first part of today's lesson at any time that you want. But at the moment, I'm trying to figure out what is t of 1, 0, 0, t of 0, 1, 0, and t of 0, 0, 1. And I have found that I can write t of 0, 0, 1 in terms of 0, 2, 3, and 2 times 0, 1, 1. So if I now plug in what those values are, what do we have here? 6, negative 5, 4, minus 2 times 3, negative 1, negative 1, right? I can figure out what is this going to come out to. This is going to be 0. So 6 minus 6 is 0. Negative 5 plus 2 is negative 3. And 4 plus 2 is 6. So there's just a little bit of arithmetic that we have to do to figure this out. Let me just write that down over here. T of 0, 0, 1 is just 0, negative 3, 6. Okay, so we had to play around a little bit to figure that out. All right, let me think for a minute. We know what T of 0, 0, 1 is now. Okay, I'm going to go ahead and erase this calculation here. Can somebody tell me, how am I going to find out? Let's do this one next. How am I going to find out T of 0, 1, 0? Can somebody suggest how I would figure that out based on what I know so far? So what do I know? I know T of 1, 2, 0, 0, 1, 1, 0, 2, 3, and now I also know T of 0, 0, 1, right? I can use that to help me, that new value, T of 0, 0, 1. Because see, if you take a look, T of 0, 1, 0 is just going to be 0, 1, 1 minus 0, 0, 1. So if you take 0, 1, 1 and you subtract 0, 0, 1, you get exactly 0, 1, 0. And T respects that subtraction.
So, Professor?
Yes?
We're allowed to reuse the one that we just found, is what you're saying?
Oh, yes, absolutely. We can use any information that we've obtained up to this point.
Oh, thank you.
That's right. Sure, you bet. Okay, so what is T of 0, 1, 0? Well, I take 3, negative 1, negative 1, and I subtract the one that I just found, which was 0, negative 3, 6, and that gives me 3, 2, negative 7. If I did the subtraction correctly, we have to subtract some negatives there. I'm going to go ahead and put that value right here. This is 3, 2, negative 7. Okay, so I now know what that number is. Okay, so this is just a little bit of scratch work down here at the bottom, right? That's kind of how we're figuring that out. Okay, again, pause if there's any questions here, guys. Finally, I need to know what is T of 1, 0, 0. T of 1, 0, 0. We need to figure this one out. Well, I know what T of 1, 2, 0 is, right? So let me put that down. T of 1, 2, 0. That's not quite the right thing, though. So from T of 1, 2, 0, I'm going to subtract something. I need to subtract T of 0, 2, 0, or in other words, 2 times T of 0, 1, 0. So if I just subtract twice of 0, 1, 0, I'll get 0, 2, 0, and I can subtract this way and plug in the values. 2, negative 1, 1, minus 2 times the quantity, well, T of 0, 1, 0, we just worked that out. It's 3, 2, negative 7. And if I now just do the subtraction, I'm going to have negative 4, comma, negative 5, comma, 1 plus 14, which is 15. So negative 4, negative 5, 15. Let me just write that right here so I can give myself room to finish the calculation. Okay, does everybody follow how I'm building 1, 0, 0, 0, 1, 0, and 0, 0, 1. I'm building those vectors out of the ones that I was given. I wasn't given the best set of vectors to work with this time, so I had to create the 1, 0, 0, 0, 1, 0, and 0, 0, 1 by doing these various linear combinations here. This could get really messy. You're going to have to trust me that I'm not going to give you one that's going to be that messy. In fact, this one is probably messier than anything you're ever going to see. I'm going to try to make it pretty obvious how to build the vectors that you want out of the vectors that I give you. So this one we had to work a little bit, but in general, It's not so terrible. Okay, so let's just write down our answer now. What is T of ABC? Well, it's just A times -4, -5, 15 plus B times 3, 2, -7 plus C times 0, -3, 6. That's it. You could leave your answer just like that if you wanted to. If you're curious, so this is a perfectly good final answer, but let me just show you. If you actually were to expand it back out again and write it as a vector, you would have -4a in the first slot here, plus 3b from the first slot of the middle term, plus nothing, comma, and then in the middle slot you have -5a from the first piece of it, plus 2b minus 3c, and then comma, and then finally 15a minus 7b plus 6c. Does everybody see where I'm getting that from? I'm literally just multiplying this linear combination out. I'm putting the a inside of the vector, the b inside of the vector, the c inside of the vector, and I'm just adding the results, right? So that's how I'm getting that. Okay. Again, for those of you who are coming in a little bit late, try not to worry too much. I'm going to post this video. You can go back and watch what you've missed from the beginning. I've just been showing a couple quick examples of how to use a linear transformation to come up with the formula for T of a vector. Okay. By the way, I mentioned something about a matrix, right? This is a transformation from R3 to R3. So there should be a 3 by 3 matrix to represent this transformation. You remember that from Tuesday? How do we come up with that matrix again? Well, what we do, it's going to be a 3 by 3. I'm just going to write it down because I want you guys to be able to see it. It's very easy to create it. What ends up happening with this matrix, T of 1, 0, 0 ends up in the first column. So that would be -4, -5, and 15. It goes right down in the first column of the matrix A. And then the second column of the matrix is just T of 0, 1, 0, which is 3, 2, -7. And then finally, T of 0, 0, 1 goes into the third column. So this is how you build this matrix capital A. Maybe I should, just for your notes, if you're following along here, let me write this down so you'll remember how we made up this matrix. We're just putting T of 1, 0, 0 in the first column, T of 0, 1, 0 in the second column, and T of 0, 0, 1 in the third column. So that is how you build that matrix. That is the matrix representation, or the matrix of the linear transformation. Okay, that's about it. Any questions on, I know that example was a little longer, but does that make sense? Anybody want to stop me to say anything about it? Because otherwise I feel pretty good. Okay, I'm going to go ahead and erase this. If I'm going too fast, you can certainly, again, watch this later on a video or take a quick picture of it and come back to it at a later time. Okay, let me go ahead and wipe this off. And guys, that's it for new material for the midterm. We've actually now covered everything, which is a breath of fresh air for me, because I just want to make sure everything's been covered, and it has now. Okay, so I guess what I'd like to do next, guys, and feel free to unmute yourself, especially during this next section. I want to see if there are any questions on the homework that you guys are doing for today. So I want to go back to chapter 5. We have homework that's due tonight, and I know a couple of you have turned it in already, but for those of you who haven't, or maybe even if you had any questions, if you have turned it in, this would be a great time to throw a question at me. Does anybody want me to go over any of the problems, the homework that's due tonight? I'll give you guys a minute to look and see. Any questions? Is everybody good?
Just a second.
All right, I'm gonna give you another minute. I know with this remote computer setup, it's a little tricky. So take your time. If you've got a question, I see Darian has a question on number 13 on section 5.3. Let me go ahead and do Darian's question right now, which is number 13 in 5.3. Okay. And this is a really good problem. I'm glad, Darian, that you asked this one, because you're going to see examples like this in the sample midterm as well. So it's good to kind of think about it. So on this problem, number 13, we have a matrix. I'll write the matrix down on the board so everybody can see it here, hopefully. 3, 1, 4, and then 1, -2, 1, and then 1, 5, 2. And they're asking us to determine orthogonal bases for the row space and column space of that matrix. Okay, so that's what they're asking. A orthogonal basis for the row space and the column space. So the first thing that we should do is just figure out what is the row space and what is the column space. Okay, so we have to go back to that. Handout, back to chapter 4. How do you find the row space of a matrix or the column space? The answer is that you have to bring this matrix to row echelon form. That's the first step for all of these kinds of questions. So let's do that. We have to do some EROs here. I'm going to try to reduce this into row echelon form. So maybe what I'll do is I'll put the, I'm going to reorder the rows a little bit so that I have a 1 in the upper left corner. So let's just put 1, -2, 1 like that. And then 3, 1, 4 is fine, and 1, 5, 2. So, so far, I just permuted rows 1 and 2. Okay. And now let me add multiples of that first row to the second and third row. I'm going to do A12 of -3 and A13 of -1. So the first row stays the same. When I multiply the first row by -3 and add it to the second row, I should get 0, 7, and 1. And when I take the negative of the first row and add it to the last row, I should get 0, 7, 1. Everybody with me? Okay, so far so good. Great. So then of course, the second and third rows are the same, so I more or less can just cross off the third row. So I have my pivots are here and here. It's perfectly fine to leave it unsimplified. You don't have to simplify it. So the row space of A, what is it? Well, it's just the span of the first row and the second row. That's just what the row space actually is equal to. This is not an orthogonal basis yet, but that is a basis. Now, guys, remember, if some of you might have done different EROs, maybe you permuted things differently or something like that, you might have a different answer. It doesn't mean that your answer is wrong. There's lots of correct answers to a problem like this. Okay, so now I'm going to label my vectors here as V1 and V2. Because I'm going to use the Gram-Schmidt process, right? When it says, if you ever see a question that's asking you to give an orthogonal basis for something, well, you just want to use the Gram-Schmidt process to orthogonalize those vectors. So let me remind you how that's going to work. W1 is the same as V1, so we don't have to do any work for that part, okay? And then the second vector, W2, is equal to, well, the answer is it's V2. I'm going to put V2 right here, minus some fraction of W1. So I'm going to put W1 right there, and I'm giving myself room to make a fraction here. So this is just from the formula. that we learned on last Thursday and last Tuesday, the Gram-Schmidt formula that's going to be on the front of your midterm exam, so you don't have to memorize it, right? So what goes on top here in this fraction is just the inner product of the two vectors that we have, right? So I'm just going to take the inner product of these two vectors. It actually brings up a question. What inner product are we supposed to use? Normally, right, the problems as they are given to you, they're going to give you an inner product that you're supposed to use. In this case, they didn't do that. So I'm just reminding you from the last couple classes where I mentioned that in the case of vectors in Rn, you should just assume that the standard inner product, the dot product, is the right one to use. Okay, if they gave you a different inner product, then you would need to work with whatever they gave you. Here they didn't give you anything, so you're just going to use the usual dot product. So I'm going to take the dot product of these vectors, which is 0, minus 14, plus 1, which is actually negative 13. Okay, and then the denominator of this fraction is just the norm of W1 squared. So I have to find the norm of W1 here and square it. It's just going to be 1 squared plus 2 squared plus 1 squared, which is 6. So we get 13 over 6 on the bottom there. So it's got a little bit of an annoying fraction to it. We have minus and negative. I guess I can rewrite this as 13 over 6 with a plus sign. So something like that. And let me just write that as a single vector before I put down my final answer. So the first slot is just 13 over 6. The second slot is, what is that? Oh boy. It's 7. Here we go. 7 minus 26 over 6 or minus 13 over 3. So that's, what is that? 21 over 3 minus 13 over 3. I think it's 8 over 3. And then finally, if you take 13 over 6 and add 1 to it, you get 19 over 6. Okay? So your basis here, your orthogonal basis, the orthogonal basis, this is for the row space. The orthogonal basis would be just W1, which is the original vector we started with, and then W2, which is 13 over 6, 8 over 3, and 19 over 6. Now, guys, this is an odd-numbered problem, and some of you might have already looked in the back of the book, and you might have noticed their answer is a little different. They actually decided to just multiply the second vector through by 6, I believe, just to get rid of the fractions. And that's fine, because all they're doing in the back of the book is they're just stretching the answer out a little bit longer. It's still orthogonal to the first vector. It's just longer than it was before. But you don't have to multiply through by 6. This is one of the challenging things about when they ask you to find some kind of a basis. There can be lots of right answers, not just the one that's in the back of the book. Okay, Darian, does that help with that problem so far? Are you following me on this?
Yeah.
Okay, great. Does anybody else have a question on this particular? Now this is just for the row space. For the column space, maybe let me just briefly remind you. Notice that the first two columns have the pivots in them. So that for the column space, let me just put it here. The column space of A would be the span of the first two columns of the original matrix. So I just want to remind you that when you're talking about column space, you do have to go back to the original matrix for that. So these, and notice I'm drawing them as columns. With the row space, I sort of drew the vectors as rows. When I'm talking about column space, I will usually draw the vectors as columns just to emphasize that we are looking at columns here. But it's important that we go back to the original two columns of the original matrix. So I'm just literally grabbing them from here, right? The first two columns of the original matrix A. Okay. Would you like me to go? So all you have to do now is that Gram-Schmidt process again with these two vectors this time. So V1 and V2, it's the same formula, and it's the same procedure. Can I let you guys, would you be okay trying that one on your own? It's basically the same thing as what we just did with the row space. Darian, is that okay with you? Okay, great. Does anybody else have any questions on any of the other problems on today's homework? I'll let you look while I'm erasing. I'm going to erase the board here. So take a look at your homework, see if there was anything else that wasn't clear, and then I'll see if you guys have any questions on it. Did anybody come up with any other problems for me to go over with you, or was it pretty good shape so far? 5.2, number 6. All right, let me go back to 5.2 and look at number 6 here. Okay, yeah, this is a good one. Thanks, Matt, for asking this one. 5.2, number 6, let's talk about it right here. I'm going to take the vector v to be the vector 7, -2. Okay? And it says, it's asking you to find all non-zero vectors W that would make the set V and W into an orthogonal set. So actually, because this is a vector in R2, we can actually draw a picture, a picture for this one. So I could draw, I'm going to just draw my XY plane here. 1, 2, 3, 4, 5, 6, 7. -2 would be this vector right here. Okay, so this is the picture of the vector V. And what this question is asking us to do is to find all ways that we could add one more vector now, so that along with V, we would have an orthogonal set, a perpendicular set, right? So that's what I'm looking for. Let me draw. We can actually see it already on the picture, right? The vectors that are perpendicular to V are going to make a right angle right there, right? So I have that blue line that sort of shows me what that would be. So the question is, well, what are the vectors that are on that blue line? They're the ones that are perpendicular to 7, -2. Now, how do we find those vectors? How do we figure out what they are? Well, I don't know what they are yet, but I can just take this blue vector and just call it AB for a minute, right? I just call it AB. And what I know is that that vector AB that I'm looking for, this is W, by the way. This will be the vector W. What I know about W is that it is perpendicular to V. And that means that the dot product should be 0, right? So I have to have a dot product of 0 here. That just means that 7A minus 2B should be equal to 0. If I dot these two vectors together, this is what I will end up with. And I'm just going to set that equal to 0. Okay? This is actually just a single equation with two unknowns in it. And I can literally imagine, I could set this up into a matrix and everything else, but there's really no need to do that. I can just imagine that B is a free variable. I'll call it T for a moment. And then I could very easily solve for A. If I solve this equation for A, I'm just going to get 2/7 of T. So this is just a single equation that has infinitely many solutions. Obviously, this blue line has infinitely many points on it, right? But specifically, it's just all of the points that have this form. So it's W could be the vector 2/7 of T, comma, T, right? And that's where T is any real number. They did emphasize that they do not want T to equal 0. That's because when we talk about vectors being orthogonal, one of the definitions in this section. For vectors to be orthogonal to each other, they have to be non-zero. Well, if I plugged 0 in for t into my vector w, I would get the 0 vector, and that's not what we want. So specifically, we should just choose all vectors of that form where t is not equal to 0. Okay, Matt, does that help? Or does anybody else have a
Yes.
question? Is that good?
But the thing is that supposed to be parentheses or the for the w vector?
Oh, right here. You know, it doesn't really matter. I'm sorry. In the book, they kind of use these interchangeably. You can draw them as points or as vectors. I actually don't care too much. This is fine. Like you can write it with parentheses.
But would you preferably write a point?
I actually don't think there is a preference. I'm going to be totally honest with you. It makes no difference. They're exactly the same thing.
Okay.
A point and a vector are like this black vector here, v. It's a vector, but it also represents a point, which is 7, -2. So whether you use parentheses or angle brackets, it makes no difference.
Okay, I got it.
Great. Okay, does anybody else have any questions on today's homework? Maybe I'll erase this one, and while I'm erasing, take a look and see if there's anything else you'd like me to go over. Did anybody get stuck on anything else? Oh, Ryuko,
15.
5.2, number 15. Yeah, let me take a look at that one. Sure thing. So on number 15, what do we have here? We have f1 of x equals 1. So they gave us some functions this time. I'm just writing them down for everybody. F of 2 of x is just equal to x, and f3 of x is just equal to 1/2 of the quantity 3x squared minus 1. Now in this section, we, in theory, have not learned the Gram-Schmidt process yet. So they're not asking us to orthogonalize anything. Instead, they're just giving us these vectors, and they're just asking us to verify that they are orthogonal. Now, they have this notation, C0 of -1, 1, that you see in the question. That is actually telling you what the vector space is that they're working in. And the inner product that they want you to use here is just the integration from -1 to 1. So let me write that down here somewhere. So the inner product. Actually, guys, to be honest with you, I would give you this inner product formula. They're assuming that you know that you're supposed to do an integral from -1 to 1 of, f of t, g of t, dt. The reason that the limits of integration are -1 to 1 this time is just because of the domain that was given right here. Okay, so because the endpoints of the interval are -1 and 1. It says, show that these functions are orthogonal. Show that they are orthogonal. So that means I have to take all of the pairwise inner products. So let me just try one of them right here, maybe. The inner product of f1 with f2. So we already know what the answer is supposed to be, right? If these vectors are really orthogonal, then the answer here that we should get should just be 0. Right? Two vectors are orthogonal when the inner product is 0. Well, let's just check it out. Integral from -1 to 1 of 1 times x, which is just x, dx. So you're just integrating x from -1 to 1. And sure enough, when you work that out, you get 1/2 x squared from -1 to 1, which is 0. So that's exactly what you wanted to get. Can you guys all see that okay? Crammed it into the corner a little bit there. Okay, so we do that, and we also have to do the inner product of of F1 with F3, we have to take every combination, right? Every pair of vectors here and calculate these inner products. So this one, this is just going to be the integral from -1 to 1 of the first polynomial times the third one, which was 1/2 of 3x squared minus 1 dx. All right, well, you just have to verify that that comes out to 0, right? So you can pull the 1/2 out. You can integrate 3x squared and get x cubed. When you integrate 1, you get x. Evaluate from -1 to 1. You're just verifying that you do get 0, okay? And then finally, the inner product of F2 with F3. Same thing, right? You integrate from -1 to 1 of the second and third polynomial. So that would be 1/2 x times 3x squared minus 1 dx. I would suggest that you multiply it out. Just throw that x inside there. So you would have the integral from -1 to 1 of 1/2 of the quantity 3x cubed minus x dx. And you should end up getting 0 out of that as well. Integrate
Can you
it.
put the screen down a little bit?
Oh, sorry.
Thank you. Yep, that's it.
Okay, great. Sorry. Yeah, so all I'm doing here, sorry, my bad. I just lost track of, I got too excited. I forgot to make sure that my camera was in view. So all we're doing here is we're just multiplying the second and third functions. So this is my original set of functions up here, right? So I'm just taking the second and third one and multiplying them together. And I'll let you guys verify. It's very easy to integrate that product and you get 0, okay? So this shows all of these zeros that we are getting, that shows that we have an orthogonal set of vectors, okay? Now, what the question's going to ask you to do is use these vectors to construct an orthonormal set of functions. So once you have an orthogonal set, it makes sense to try to build an orthonormal set. And we talked about this before, right? The way that we do this is we simply divide each vector by its norm. So I need to figure out the norm of each one of my vectors. Let me come back over here. So like, for example, the norm of F1. Let me make sure you can see this. Sorry, I'm going to move this again. Let me just set it back slightly. Let me just see what I've got here. So I'm sorry, I started writing over on the left side. I'm going to calculate the norm of F1 here. Okay. So remember the formula. This is the square root of the inner product of F1 with itself. Okay. So what is that going to give me? Well, this is the square root of the integral from -1 to 1 of F1 times itself. Well, that's just 1 times dx, right? So actually, I don't really need much room for this. Let me just put it right here. This is just the square root of the integral from -1 to 1 of dx, and that gives me the square root of 2. When you integrate dx and evaluate it from -1 to 1, you'll get 2, and that's underneath that radical. I'm going to go ahead and erase the right side of this board. I'm sorry, I wish I had a bigger board, but we're just going to have to make do. Okay, so for example, this means that U1 is going to be 1 over radical 2, right? So the unit vector that we're replacing F1 with is just U1, and you get it by taking the F1 and dividing by its norm, which is the square root of 2. So we get 1 over the square root of 2 for the first one. Let me do the second one for you as well, just to make sure everybody's on the same page. The norm of F2, this is just the square root of the inner product of F2 with itself. And so that's just the square root of the integral from -1 to 1 of x times x. So that would be x squared dx. And when you integrate x squared, of course, you get 1/3 of x cubed. So we're going to get 1/3 of x cubed. I'll write that down. 1/3 of x cubed, which we evaluate from -1 to 1. And I think that comes out to 2/3. That's 1/3 minus negative 1/3. So this is the square root of 2/3. Okay. So that's what we have to divide by to get our second unit vector. So let me write it up here. The second unit vector then becomes x divided by the square root of 2/3, which I'm going to write as the square root of 3/2. In other words, I'm going to flip it over. This fractional radical, I'm flipping it over to the square root of 3/2. Okay, so these are the first two unit vectors. And then from there, we just have to do the third one. The third one is going to be a little more tedious. Ryuko, are you getting the idea here? Let me ask you this. Does anybody want me to work out this third one, or do you have the idea and you just want to work it out on your own? Does anybody want me to do the third one? It's the same exact thing. The integral will be a little bit messier. So you'll have to like take the square root of the integral from -1 to 1 of, well, it'll be something like 1/4 of 3x squared minus 1 squared dx. So you'll actually want to square this out. You'll actually want to square out that perfect square before you actually do the integral. But there's absolutely nothing difficult about this. It's just a slightly tedious calculation. Great. Okay. Does anybody have any other questions on anything else from today's homework assignment? Let me erase the board in the meantime. Take another look and make sure that there's nothing else that you're bothered about. Nothing too bad. Okay. If there's, yeah, so the question is, what else am I going to do today for the rest of the time? We don't have a massive amount of time. What I was going to do was I was going to work through with you guys a few of the items from these last two group works that we didn't, of course, get to do in class. And I thought it might be useful to look at a couple of them together just to talk them through, just kind of in the spirit of virtual office hours. So why don't I move in that direction right now? It sounds like we're in pretty good shape on the homework. Maybe I'll do, I'm not going to maybe do all these problems from the group work today because I can also do some of them later. But let me do a couple of problems from the group works that I think might be a little more challenging that people might want to see. And then I'll come back and give you one more chance to ask if there's anything else on the homework that we didn't quite cover yet. Okay, does that sound like a game plan maybe? I think that might be good. So I'm gonna, of course, give you a occasional conceptual question on the midterm. So I'm gonna give you a couple of little conceptual questions right now that I think would be good for you to understand, okay? So these are coming from the group work. I'll just say GW number 8. I'm gonna work on problem number 4 from that group work right now, okay? And it just says to explain these facts. So what are we explaining? The first one says if A is m by n with column space of A equal to the null space of A. So this is like a theoretical question that I could put like on a test or something. This is something I want everybody to understand. So then we're going to try to explain, why does m have to equal n? Okay, so let's make sure that everybody's able to catch that. Okay, so this is a true statement. If we have a matrix whose column space is the same as its null space, then it actually has to be a square matrix. And the reason I like this question is it makes us remember some things about column space, row space, null space, right? The relationship and stuff. So let's think about that for a minute. Does anybody have any ideas? If we were in class, we would do this as a group work. So I'd give you guys lots of time to talk about it with each other. Does anybody have any thoughts about this one, though, that they'd like to share? I'm looking for that handout. I hope that you all still have that recap summary handout from sections 4.6, 4.8, and 4.9. There is a lot of good stuff on that in terms of trying to understand the highlights of chapter 4. And one of the things on that handout is the second hand. Are you guys able to see okay? Is it just the, maybe I need to move a little closer here. Matt, is the print just too small? Is that the problem? Or I'm just sitting in the way of it, maybe?
I think it's just my computer. It's just pitch black for some reason.
Oh, your whole screen went black. Okay, well, I don't know what to tell you about that part. I can still see everybody else is doing okay, it looks like, for now. If you're wondering what I'm looking at, Matt, in case you can't get your screen back, I'm just looking at the last problem on group work number 8. So you can find that online and just kind of follow along with my voice a little bit. And then hopefully you'll get to look at this video later. Does anybody have any thoughts about why this matrix would have to be a square size? This is definitely in the realm of conceptual questions, and it definitely is related to what's on that recap summary handout that I passed out, or that my sub passed out or something towards the beginning of the month.
Hi, Professor.
Yes.
I just restarted my Zoom, so I missed everything that you said.
Oh, I'm not saying much. I'm just all I've been saying is that to explain this problem, the stuff that's on that recap summary of sections 4.6, 4.8, and 4.9, that stuff is really handy for this. So
Okay.
guys, tell me, for example, the column space of A, what is that a subspace of? You can unmute yourself. Some of you guys are quiet in the background. It's totally okay if you want to speak up. This is a subspace of what? The column space of A. If we have an M by N matrix here, M rows and N columns, right? The columns here, how many entries does each column of this matrix have? Well, the answer is there are exactly, there are M slots there. This is a subspace of Rm, right? The column space is always a subspace of Rm. What about the null space? Do you remember what the null space is a subspace of?
Said how many ranks there are?
The dimension of the null space is the number of unpivoted columns in the matrix, in the row echelon form of the matrix. But in terms of just what it's a subspace of, is it Rm or is it Rn? The null space.
Rn?
It's Rn. You guys can cheat and I won't even know. You just have to pull out that handout that has the information on it. It's a subspace of Rn, right? It's a subspace of Rn. Let me make sure I'm not blocking the screen here. So the point here, guys, is that the column space is a subspace of Rm, and the null space is a subspace of Rn. So if those two spaces are the same for a particular matrix, if we have a matrix where the column space and the null space end up being exactly the same set of vectors, well, then the M and the N have to be identical. Okay, let me write down it's basically just a little one-line explanation here. So the reason, let me just put this over here so everybody can see this. Okay, what's the reason for this? It's just basically because the call space of A is a subspace of Rm, and the null space of A is a subspace of Rn. Thus, M equals N. They both have to be compatible. Both of those spaces have to have the same number of slots in this case. Okay, great. So that's the explanation for that one. Now I'm going to give you another one. If everybody's okay with that one, I'm going to write down a second one. Okay, I'll put it over here on the right in case you're still trying to copy the first one. So part B of the same exact group work just says if A is n by n. So let's suppose we have a square matrix this time. If A is n by n with the row space of A equal to the null space of A. So if the row space and the null space are equal, then we want to explain why A cannot be invertible. Cannot be invertible. This is a really nice problem too, to understand kind of a lot of the material in the end of chapter 4. So let's take a quick thought process through this as well. If we have a matrix whose row space and null space are equal, then that matrix cannot be invertible. Okay? So the row space and null space are both subspaces of Rn. So in this case, we're not talking about the difference between M and N. In fact, we have a square matrix. So there's only one dimension here, which is the N value, right? But I want you to think with me for a second. If A is invertible, after all, right? Now, I'm kind of doing this by like a contradiction approach. I'm saying, well, what if A was invertible? What would go wrong? Can somebody tell me what the null space of an invertible matrix is? For an invertible matrix, we know something about the null space of it. So if you go back into the back cover of the book, you see this, I don't know if you can see what I'm trying to show you here. This is the invertible matrix theorem. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. I think we got up to at least P already, right? All of those things that are equivalent. I want you to look at that before the midterm. I want you to be familiar with all of those statements in that invertible matrix theorem. So for an invertible matrix, one of the items in that list is that for an invertible matrix, the null space is just the zero vector, right? For an invertible matrix, there is no null space. The nullity is 0, right? And the null space has nothing in it. So imagine if you had an invertible matrix, the null space would be 0, but we've just assumed that the row space is the same as the null space. So in that case, we would be then saying that the row space of A, can everybody read this? The row space of A would be the zero vector. The span of the rows would be the zero vector. Well, what kind of a matrix would that be? What kind of a matrix could you have where if you take all of the rows and form their span, you get nothing? There's only one matrix that would have a trivial row space, and that is a matrix of all zeros, right? I'll just put some dots here. This is a matrix of all zeros. If the row space is just the zero vector, then you don't have any numbers in that matrix at all. It's just all zeros. And that, of course, would be completely contrary to what we said here, which was that A is invertible, right? So this is, I'm just going to say this is a contradiction. This is like a little proof. It's just a little proof to try to explain why a matrix that's invertible would not have the same row space and null space. And it's a good reminder to you guys as you're studying for the exam. It's a good reminder as you're studying for the exam to review the invertible matrix theorem. It's got a lot of stuff in it about the null space, the row space, the column space, and how they're related to each other. For an invertible matrix, the null space is tiny, right? It's just the zero vector only. But for an invertible matrix, the row space and column space are all of Rn, right? Those things are all listed in that theorem. So it's good to refresh your memory about that. I'm going to want you to know, for an invertible matrix, what can you say about the null space, row space, and column space before you even look at the matrix? If you know it's invertible, that invertible matrix theorem will help you out. Okay? Are there any questions about these two items here? Okay, if not, let me just give you a couple more of these. We'll probably stop early today, by the way, guys. I know I don't very often say that. But I just want to go through a couple more things that I think would be really good practice for the midterm. So again, this is just a informal time. And if anybody's found another homework problem they want me to do, you can also throw that up there. But let me try this one. Try this one with you. This is number 3 on the same group work. And all this says is find the nullity. Find the nullity of this matrix capital A. And again, if you don't want to write this all down, you certainly could just go to the group work itself and find these problems. Okay, so it's going to be something like this. So there's a 3x4 matrix, and it's asking us to find the nullity, but I want to add a little bit to that. Let's find it by inspection. Let's not even do the EROs. Let's not even like work very hard at it. Just look at it. Can you tell me just by looking at it what the nullity is? This is a quick one. This is a really, really quick one. You just look at the matrix and say, aha, I see something about the matrix that I can use. And so I immediately know what the nullity is going to be. Does anybody have a thought?
Is it 3?
Hey, who said that?
Can I?
Well, you're right. It is definitely 3. You can just look at it and see that it's 3. Guys, take a look. All 3 rows are just multiples of the first row. You're going to have just one pivot. So the rank is 1. So let me just write this down. The rank is 1. We can just see that. And we remember the rank nullity theorem, right? When we take the rank and we add the nullity to it, the nullity is 3 because the total comes out to 4 columns, right? So that's exactly right. Sometimes you can just look at the matrix and you know the answer immediately. Okay? All right, let's do one more, okay? That was fast. I'm gonna do one more and then we'll call it a day. This one's a little bit more work. I'm kind of going backwards. I don't know why. Number 2 says find a basis. Find a basis for the subspace. For the subspace, I'm going to call it S of M3 of R. So these would be the 3x3 matrices whose entries sum to 0. And what I want to do is find a basis for that and then also find the dimension of S. So this is taking us back a little bit. We are simply reviewing for the midterm right now, guys. This is just an old problem that I think would be good to be thinking about. We still have a whole week to study. So heck, let's get ahead of the game and try this problem now. Okay. So I've given you a subspace. The 3 by 3 matrices, of course, that whole space would be dimension 9, but we're not talking about the whole M3 by 3 of R right now. We're only looking at the 3 by 3 matrices whose entries add up to 0. Can somebody tell me what I might want to do first? You can unmute yourself if you have an idea, and I would love to hear your ideas. What should we do first to try to get a handle on this? The 3 by 3 matrices whose entries, by entries I mean all 9 entries, add up to 0. If you kind of imagine, yeah, go ahead, Matt.
Okay, first row A, B, negative A plus B.
Okay,
And then,
hold on just a second, Matt. Great idea. So we're starting to fill out the form of this matrix, and this is exactly the right thing to do. So this is excellent. Now, the question in this case does not say that each row has to add up to 0. I know we've done a couple examples in the past where I said something like the rows have to add up to 0 or the columns have to add up to 0. Here, I'm not requiring that. So I would argue that the third entry in the first row can be any other number that we want as well. Like I could put a C there.
so
A, B,
and
C.
then D, E, F, and then G, H, and then negative, all of them added together.
That's it. That's it. It's just A, B, C, D, E, F, G, H, and then the negative of all of those added together in the far bottom right corner. This is a key step, guys. This is the form of a matrix in S. I'm calling it capital A. This is my matrix. This is what it looks like. Okay. Now from there, once I have the form written down, how do I get the basis? Let me see if I can hear from, just a second. I want to just see if I can hear from somebody I haven't heard from yet. Jay, are you there? It says you're here. Jay, are you there? No, Jay?
Hello, sorry.
Oh, Jay, is that you?
Yep.
Do you have an idea here? Sorry, I didn't mean to pick on you. I just saw that you were in the room.
No, sorry. I was actually just in the restroom, so I missed what you were.
Okay, let me see. Randy, do you have an idea? How do we get a basis? Once we write down the form of the vector, what do we do to get the actual basis?
Hello?
Hey, Randy, I can hear you.
Okay. What was that again?
Yeah. Oh, I was just asking, how would you get the basis for S? If I have the form of my matrix like this, A, B, C, D, E, F, G, H, and then the negative of everything added together, how do we get a basis for that?
You bust out the variables?
That's the answer. Exactly, you bust out the variables. So that's exactly right. So if I bust out the variables, I can actually immediately write down the basis. I'm going to start writing it here. So when I bust out the A, right, I see there's a 1 right there, and there's a -1 in the far lower right corner. And everything else, all the rest of the entries do not have an A in them, so those would all be 0. Right? Can everybody see that all right? So we have the first matrix there. Now, to get the second matrix in the basis, I'm going to come over to this side so I can write another one. I'm going to bust out the B. When I bust out the B, I have to look, where is my B in the matrix? I have one B at the top middle, and I have a -B in the lower right corner. Everything else is all zeros. And I'm just going to put ... here. We're not going to write them all out. The last one that we would have to write down would be when we bust out the H. When I bust out the H, I'm going to get a lot of zeros in the first 2 rows. And then the last row is 0, 1, and -1. That's your basis. Okay, so this is good practice. We've done a few of these before where you write down the form of the vector. That's really important here. And then you just bust out the variables and make your list. Be sure to use these, squiggly braces to denote your basis. That's very handy. So let me see. Can somebody tell me based on this? Javier, are you there? Hold on. Give me a second. I just want to ask you what the dimension of this is.
Yeah, I'm here.
Oh, great. Awesome. Can you tell me what the dimension of this set S is going to be?
Set S.
Yeah, how many basis vectors am I going to have down here?
Let's see. 2.
Well, I've listed already. So here's the first one. I busted out the A and I got this matrix. Here's the second one. I busted out the B and I got this matrix.
Yeah.
And then I have all this dot, dot, dot business here.
Mm-hmm.
And then this is going to be the last one over here when I bust out the H. How many variables do I have to bust out?
H variables, right?
Well, how many? I'm looking for a number. So how many different variables
1,
do you
2,
see?
3, 4, 5, 6. 8.
There's 8 of them, and that is the right answer. Exactly.
Okay.
The dimension.
Okay.
Does that make sense?
Yeah, yeah. Oh, okay.
The dimension of S is equal to 8. This is an 8-dimensional subspace of M3 of R.
Mm-hmm.
M3 of R, of course, is 9-dimensional. So this is just an 8-dimensional subspace of that.
Okay.
Okay. Does this
Okay,
make,
got it. Yeah.
does anybody have any questions on this? This is how this example works. And almost all of these problems, you have to write down the form of the vector first, and then bust out the variables and make your list of the basis vectors. Okay. Any other questions about any of those ideas so far?
So, Professor?
Yes, Ryoko.
Oh, the reason why it's total all the way up to H is because you said all the entries have to equal 0, not just like the rows or columns.
That's exactly right. Very good point.
Yeah.
Let me just emphasize that. So we're not saying that the rows have to add up to 0 or the columns have to add up to 0 or anything like that. We're just saying all 9 numbers, the whole entries of the whole matrix, have to add up to 0. And what that really means is that you can choose 8 of those 9 numbers to be anything you want. And then the very last entry in the lower right corner has to cancel everything out, right? So that the whole thing adds up to 0. So yeah, you have to read these questions very carefully as to exactly what the condition is. Because yeah, the condition makes a big difference, okay? If we're taking the exam next Thursday and you're not quite clear about a particular question, right? Feel free to ask me a question. Like I'm going to be in the Zoom room with you guys throughout the exam, and I'll be happy to clarify anything. If sometimes the wording, you have to look really carefully what it's actually saying. Okay. I've got a few more I could do, but I think I'm gonna wait. Maybe we'll talk about a few more of them on Tuesday. I think we've done pretty well today. Did anybody come up with any other questions from the homework that they wanted me to go over? Okay, if not, I think I'm gonna go ahead and sort of end this session. Back when we were in the classroom, we always took a 10-minute break in the middle, and I've been forgetting about that. So I think what I'll do, we'll just quit like 10 minutes early. We only have about another 10 minutes anyway till technically we're done. But I've covered everything I think I need to cover. Between now and Tuesday, if you have questions about the homework that's coming up, or if you do some studying for the midterm and you want to ask me some questions, just feel free to come to any of my virtual office hours. Or if you don't want to make those hours, you can also shoot me an email. We can set up another time to talk. I've got a lot of availability between now and your midterm next Thursday. So by all means, feel free to reach out to me. I'm going to actually go into my office hours meeting room at 2 o'clock. So you can always come over there and talk to me some more then, or later on tonight, I'll be around. Please know that I am still in touch with you, even if I'm not physically with you. I want to show you something before we go, by the way. I want to show you where I'm at. I'm out in the mountains, and I don't know if you can see out my window. It is snowing like cats and dogs snowing out there. This is out on the back porch of my house. So you guys, I hope you're enjoying sunny California. It's probably a little nicer than it is here, but it's a good enough reason for me to just, I guess, stay indoors and do math. So, oh, it's raining there? Oh, that's too bad. Well, rain is a little bit easier to drive in than snow, believe it or not. So I'm stuck at this house for like the foreseeable future. I would love nothing more than to talk to you guys about math and see what you're up to. Yeah, so anyway, that's all I've got for today. I'm going to go ahead and end the meeting. You can rewatch any part of this again if you came in late or have questions. I'm going to post this video and we will be able to follow up and watch it again if we need to. So thanks for coming today, guys. I will see you again soon.